Okay, let's do the next topic, air masses. So we just finished up talking about pressure systems, wind. So now we want to talk about, well, if air has certain characteristics or variables like moisture and temperature, how does that look at like the broader, more regional aspects of weather? That's where we come into air masses. So we've got several conditions that make an air mass an air mass. I know it doesn't sound quite right, but an air mass must have uniform temperature, pressure, and moisture conditions when we label or we identify an air mass. Now, the way those air masses move dictates whether or not we have weather fronts. Okay? Within those air masses, we may also have pressure systems, like a high or a low pressure. Now, an air mass, let's pretend I am a cold air mass. In my blue shirt, I am a big cold air mass. I'm going to say I'm a cold, dry air mass. Yep, I need some lotion on these hands. All right, so cold air mass. If I'm an air mass that's moving into a place within the country, the front of me is maybe moving into an area that's warmer. So let's say this room I'm moving into is warmer, so the front of me is interacting with the warm air in front of me. And as I move, it forces that warm air up in front of me. Right? Because I'm cold, I can get underneath that air. So I am the front of an air mass. So when you're watching the weather and they talk about weather fronts, we're saying in the weather business that the front is the front of an air mass behind it. So a cold front has a cold air mass behind it. A warm front has a warm air mass behind it. Okay? So let's not get too complicated just yet. Now, in air masses, we have different coding systems. There's codes for everything in earth science, right? Because you have to build that infinite knowledge of earth science, all right? For all of them questions. Continental. Continental tends to be a lowercase c. Continental means it's over land, meaning that air is dry. There's no water underneath, it's land, it's dry air. Okay? Maritime. Maritime means the ocean. Marina, maritime. Over water. Usually large bodies of water like the ocean. But that will cause the air to have moisture. And it will be humid. Polar. This means we're forming at high latitudes, closer to the poles. Maybe the North Pole or the South Pole. By the way, that polar air is going to be cold. Tropical, T. You're happening at the lower latitudes closer to the equator. Okay? Now that's going to be warm air. And then combination of these. Sometimes we have land at the equator. We have water at the equator. That's going to combine these abbreviations in order to tell us what the air mass fully consists of. All right? Let's look. So continental polar, CP, lowercase c, capital P. Continental polar means cold and dry air mass that forms over high latitude land. Continental, land, dry. Polar, cold, at the poles. So land near the poles, like Antarctica or northern Canada, Alaska, Siberia. Those areas will be continental polar air masses forming above them. Continental tropical, you're talking about deserts like the Sahara, which is near the equator and it's dry. You're talking about the Mojave Desert in the southwest United States. You're talking about the outback in Australia and the Gobi Desert when we're talking about China. Those areas are at lower latitudes, warmer, and over land, so you've got continental tropical. Maritime polar, cold ocean. North Atlantic, South Atlantic, near the poles. You're also talking about North Pacific, South Pacific, near the poles. All right? We actually have the Arctic Ocean and the Antarctic or Southern Ocean. All right, MT, maritime tropical. You're at the equator, central, right at the equator, or within the latitudes that are tropical. The Tropic of Cancer, the Tropic of Capricorn. In there, you've got your tropical air. And if it's over water, it's maritime, so MT. So in your own words, I want you to stop and jot. Start thinking about, in your own words, what is an air mass? How can you describe it? I also want you to think about what are two characteristics that we discussed that make up and describe any air mass. Lastly, I want you to determine, based on all the resources on Earth, what is the greatest source of moisture for all the air on this planet. So pause, stop and jot, and then we'll talk about it. Okay, so not much of a pause for me because you know how I go. I keep ripping at this thing, but you at least get to hit the pause button. So here, in your own words, I'm going to leave that as such, in your own words. But in my own words, an air mass is a amount of air that has similar temperature, pressure, and moisture conditions. And those moisture conditions and temperature conditions can vary depending on where on the planet you are. Now, two characteristics of any air mass: it has to be similar temperature, similar moisture conditions. Okay? Pressure can alter a little. What is the greatest source? The ocean. So down here, I've got a map that shows you generally where we have certain air masses forming on the planet. So you can see your MTs, your CTs, your CPs, your MPs, your CTs, your MTs. Oh, that's an ME. That means maritime equatorial, like right at the equator. A CA up here is continental Arctic, down here continental Antarctic. So they do give some more specific codes to those, but typically we can still kind of refer to them as CPs or CP or MPs. So next, what I'd like you to do, I'd like you to stop and I'd like you to jot down some information from before, start recognizing what the characteristics, origins, and the name of these symbols are here, and attempt to fill this in. Pause it up. You know I don't get the pause, I just gotta keep rolling and make sure these videos aren't too long. Don't complain, I already know you think these videos are too long, but think about it. You don't have to you could speed me up if you want. You could do 1.5x, right? Quit your complaining. All right, so here we go. Hopefully you've paused and you've done this, but MT, maritime tropical. I'm not writing this stuff out, I'm gonna save some time. So maritime tropical, maritime polar, continental tropical, continental polar. The origin, okay? MT, it's over water, low latitudes. MP, over water, high latitudes. CT, over land, low latitudes. CP, over land, high latitudes. Characteristics, this is going to be MT is warm and moist. MP, cold and moist. CT, that's right, dry and warm. CP, dry and cold. All right, so we have at least some of these things mapped out so we understand what it looks like and what it means. Now we got to get it onto the map. I do want you to be careful though. When I was referring to it being cold and moist, or warm and moist, or I was saying maybe cold and dry, I know I'm referring to the temperature first, but remember that the lowercase code dictates whether it's wet or dry. So if you're uncomfortable with remembering that and saying it the other way, go ahead and say moist and warm, moist and cold, dry and warm, dry and cold. All right, let's get these things on the map. So here we go. Down here, we're near low latitudes. This is the southern United States. You've seen North America 100 times this year. So here at low latitudes, we've got MT, because it's warm. So we have warm, we have moist and warm. Up here, we're going to have moist and cold, MP. Here, we're going to have CP, because we're over land, continental, polar. MP, MT, even in here, the Caribbean and the Gulf of Mexico, MT. And you can see in here, this is a CT that they've labeled already for you in here. All right, this one you should be able to answer on your own. Stop and jot, practice that one out. CA, if you need to, refer back to the map on this page 10. All right, so before we get into independent practice series, one more topic I'd like to refer to so that we can understand how fronts continue to enhance and help us understand the weather. All right, so cloud formation. We've got to talk about the fact that warm air is rising in a low pressure, and that will result in creating clouds. So back to the front. I am a cold air mass. Here is the front of me. And as I move through, I push things out of the way. And as I push the air out of the way, that air is going to rise up because I'm going to get up and underneath it. All right? So we've got an acronym here to help us understand the formation of clouds. It's pronounced REC, but you can't write WRECCC on Regents. So warm air rises, expands, cools, condenses, then you have clouds. That's a great acronym to start practicing every time that you have to answer anything that deals with weather. All right, so here we've got that warm ground, that warm air starts to rise up. As it gets a little bit higher, you've got some cooling that takes place. You also have some expansion, right? And that expansion also helps with the cooling process of moving air further away from itself, up high, because that's a little counterintuitive, is that we think that when air expands, that it's high, but it doesn't always stay high. Once it's expanded up there, that air molecules are spread out because there's less air up there. And that water vapor is going to try to find a way to condense together because that air is moving away from it and not keeping it warm anymore. As that condenses, it then forms those cloud droplets. But what does it form a cloud droplet around? Well, clouds can't just form out of nowhere, so we do need condensation nuclei. So there has to be something like dust or pollen or smoke or ash, something that naturally occurs in the air for there to be a surface that water will condense on. I mean, think about it in the bathroom. You take a really hot shower, the room is kind of cold, you kept the door shut, maybe you don't have a fan, or you didn't turn the fan on, or you didn't open the window, and then that hot, moist air builds up inside that bathroom. You get out, the mirror is covered in water. The window is covered in water. Maybe even the walls are covered in water. It depends on if you took a really long, hot shower. Now, that surface of the mirror, that surface of the window or the wall, that is the nuclei. That's the location where water can condense and sit on. It has a location. Okay? It's not going to form a cloud that's going to rain inside your bathroom, but you certainly are going to have instances where that heat's being extracted out of the gas, the water vapor, at the surface of the mirror, and it condenses right on the mirror. So we need these substances in the air for condensation and clouds to form, thus providing us rain and fresh water. Okay? Rain is a good thing. Don't forget that. All right? Too much rain, too much of any good thing is not a good thing. All right? But anyways, so back here, we've got our reminder that we're dealing with convection cells. But we're going to see how now air falls in a high pressure. It fills into a low pressure, and then that air rises up in a low pressure and spreads out to finish the convection cell. So that air sinks to the high pressure, like we learned with all the paper that went flying, and then the air goes into the low pressure, up into the sky, makes clouds because, you know it, because we just covered it. REC is occurring as it's rising to create those clouds, precipitation, and then that air after it's been wrung out, for lack of better words, precipitation is complete, the humidity drops, that air starts to cool down, move over, and converge above and sink for high pressure. All right, so warm air could rise near a cold, warm, or occluded fronts. So different frontal symbols are indicating that air is being pushed up and the REC process is occurring. Okay? So along that cold front, like me, the cold front, or dry, cold air mass is moving into an area that's warm, it's going to push that air up. So you're getting that warm air that's in front of the cold front. It's going to rise. It's going to do a little expansion. It's going to start to cool. It's going to find a condensation nuclei and form around that condensation nuclei and eventually become clouds right at the leading front of my air mass. So an example here, we have our CP. Our CP is moving in and it's hitting our MT and it's forcing this to rack. And as it gets racked, especially along the cold front, it gets violent. The air is moving up very quickly and it's fueling thunderstorms. So these cold fronts are usually what we have to be careful of, especially come springtime, in the summertime. They have the potential to make some very severe storms. So these are the ones where we're going to get thunderstorms, hail, tornadoes. They come out of cold fronts. Now, as maybe a warm front is catching up behind me, because as my air mass, I'm only as big as I am, right? And as my air mass is moving away, something's got to fill in behind me. And usually behind is going to be the opposite air mass potentially. Especially if we're dealing with a seasonal change like the springtime, where you're going to get a real switch between your warm and your cold air masses. I mean, think about the fact that we've got 70-degree days, and then we go down to like 50-degree days, and then we're kind of up to 67 and down to 44. Those air masses are moving through, and another one is filling in behind it. So in the second case here, if a warm air mass is filling in behind me, it's kind of trying to catch up, and if it's going too fast, it might be moving up my backside and rising up that air. And so it's not going to do it as violently as me pushing it up. But you will get some gentle rack up the backside of a cold CP. So this might be another MT, and then this is a CP, and you get some rack. Not violent like before the cold front, but you get rack here. So you get those regional rains, those long drizzly days where it just feels like it goes on for like 3 or 4 days. And I know it's probably going to be a little tough because we're going to be going into April soon, and you know that old saying, April showers bring May flowers. So we're going to probably see a lot of these combined together during April. So hang in there, all right? There are two more fronts that occur where if a cold front catches up to a warm front, and then they both catch up to a back of a cold front or a cold air mass, you end up with an occluded front, where you have both a cold and a warm meeting up. So here we've got WRECCC, REC, taking place here, but you're also going to have REC occurring here because they are catching up to each other. So you might have this regional rainfall coming into the area for a couple of days, and it's followed up without a break into some thunder showers. And then maybe by like the second or third day, depending on how slow this front is moving. All right, so that's an occluded front. And then you get these ones, stationaries. You want to have rain for 5 days straight, then you need a stationary front. This sucker don't want to move. It's like molasses in January. So here, instead, we end up having a collision where they're meeting and getting stuck. And the only way that they're going to get past is if they start to slide past each other eventually. Or that whole system just eventually moves out on its own because the planetary winds and Coriolis are shoving it off to the northeast. So stationaries. I like rain, but I dread stationary fronts. You see a stationary front, and there's nowhere to run. All right, let's talk about another way for REC to occur, but this time we're going to talk about the orographic effect. All right, so this is a mountain range, a physical barrier, not just density of air affecting where everything's going to move, but now we're dealing with a physical barrier where that air is going to get ramped up the side of a mountain. So here, we've got a mountain in the way, and as that air from a warm, maybe a more moist and tropical region, maybe like the West Coast, California. These could be like the Rockies. You've got wreck taking place up the side of this mountain, creating weather here. And it rains and rains and rains and rains, and eventually that air makes it over the top and starts coming down the other side, and it's dry. So over here we might be dealing with maybe like a CT. Okay. Now, as it's rising, that air is cooling, it's condensing, you get clouds, you get rain, and eventually it's over here where it's cool. Cool air is at the top. But as it sinks, the air is no longer being expanded. It's being pushed together and bouncing around each other more. And as it bounces around, there's more friction. So that air, as it sinks, starts to warm up a little bit. Okay? We're not talking about the moisture. Over here, there's two components. You've got air molecules and you've got water vapor molecules. You've got O2, you've got carbon dioxide, you've got nitrogen. But there's also water vapor here. That water vapor condenses. That's what comes and sticks together. Okay? And over here, that's just the air. You have very little water vapor. And that air, just the air, as it comes down, starts to get closer together and moving around, creating the friction and the heat. Okay? So this is the orographic effect. This is the windward side. And over here, this is called the leeward side. It also means that this is the rain shadow. Right? The absence of rain. All right. If you'd like, here's a challenge for those of you that would like to be challenged a little bit. If you'd like to send this to me through Jupiter, I can award you a few extra class participation points towards your mark. If you're great, if you want to give this one a shot. But otherwise, let's move on to here. So now let's start talking about how there are fronts as part of a synoptic map. So this is a synoptic map. So AKA a weather map now. So we've got station models here. We've got air mass codes. We've got pressure symbols. We have frontal systems. Now let's go back just to make sure that we understand what these symbols are and how I know what they are before we get real deep into talk about either side. So on page 13 of your reference tables, you've got an area for your air masses and your fronts so that you can identify the names based on the two coded symbol for air masses. You've got fronts where you've got what each symbol means. You're going to have to do some memorization of what the conditions are behind each or when each of them meet one another. But they are here in case you need to recall them. So looking at this map, we have a lot going on. Just to remind you, this is the eastern half of the United States. We've got our low pressure here and a frontal system. We have a cold front here with the arrows pointing the direction that the front is going. We have a warm front here with the half circles pointing in the direction it is going. And now we can begin to talk about why it's drawn this way. So warm fronts and cold fronts tend to stem out of a low pressure system. Because as a low pressure system, we know that it's rotating. Ooh, I'm going to change the color. Let's do red. It's rotating counterclockwise. So as this thing is rotating, it's pulling air in from the ocean, and it's also pulling down the air from Canada, which is cold. So we've got the warm air being pulled up here, the cold air being pulled down south this way. So you can see that as it's pulling in a counterclockwise rotational direction. Okay. For our high pressure, we've got clockwise. You can almost think of these things kind of like gears, where they kind of mesh together kind of well. All right, we've got our CP, we've got our MT, so we know the conditions behind the front, cold and dry. We know that behind this front here, we have warm and moist. It's also important to note that over here, we've got also CP in this region here. So we've got cold, dry air mass of land up here that our MT is interacting with. Okay. We have station models. I'm going to keep diving deeper, drilling deeper into this thing. So now we've got station models with different cities showing different conditions on either side of those station models. So for instance, St. Louis, you've got temperature, dew point, pressure, you've got cloud cover, you've got wind, speed, and direction. So you'll need page 13 for station models if you need to refresh your memory on that. Okay. You've got on this side of the MT showing you temperatures, again pressures, cloud conditions, and wind speed and directions. What's going to be important in terms of completing those questions below is making sure that you realize that there are relationships still between temperature and dew point, making predictions of what happens as these fronts are moving around the low pressure, what happens to the conditions of weather eventually in Atlanta, maybe eventually the conditions in, that's in Mobile, Alabama, there's Jacksonville. You might want to talk about what happens to conditions in Buffalo or New York City as this thing sweeps through in terms of not just temperature, but also what might happen in terms of the weather and precipitation. So pause the video, try to answer some of these questions here before we go into a more guided practice. Okay, so I know that you're noticing that we're doing a lot of these, but before our guided practice, independent practice. However, I'd like to point out that this would be our guided and independent practice on one day, and then we'd have our follow-up questions the next day with yet another small mini lesson. But I'm compiling all of this to make it more condensed and hopefully easier to watch everything and stop and go as you are working. Okay, let's get at it before this bell rings in a few minutes. So, what is the wind speed and direction in Jacksonville? Well, here we go. That's Jacksonville. Direction, wind speed. So it is 5 knots because it's indented and it's from the, because it's North America, that's north. So it's coming from the southwest. Okay, it's pointing that way. So what is the relative humidity in Mobile, Alabama? All right, well, let's take a look. We've got, looks like 74 and 73. Chances are that you're somewhere between 90 and 100% relative humidity, because as we recall from practice, if both of these values are exactly the same, you have 100% relative humidity. That's temperature and dew point. That air cooled down, hit dew point, squeezed the water, condensed it, got it out. All right? All that water condensed on itself. So where did the air currently over Riley originate? So here's Riley, MT. It originated over tropical water. Okay? What are the characteristics of that air mass? Warm and moist. Okay? Where did the air originate over St. Louis? So here's St. Louis. CP. It originally formed over cool land. So it's a continental polar. You could maybe even say that it might have came over from Canada if you want to get real specific. Okay. What are the characteristics of this air mass? All right, so it's going to be dry and cold. What will happen to temperature in Atlanta over the next several hours? So here is Atlanta. Eventually, the cold front will pass it as the whole thing rotates. Atlanta will become cooler and experience rain. And I say rain because the temperatures over here are above freezing. What will happen to the temperatures in New York over the next several hours? So here's New York. It will experience warmer temperatures. And also rain. So let's go to our fronts and cloud development, guided and independent practice. If you need to get it out, you can go to your Google Drive, not Castle, Google Drive, and the shared folder, pull out the fronts and cloud development independent guide practice. If you need the access points, you will use this one, okay? So pause the video, try out question 1, try out question 2, and go ahead, pause the video. All right, so you've had an opportunity to pause the video. Let's read through question 1. We've got figure 1. Base your answer to the question on the weather map below, which represents a low pressure system over New York State. The low pressure on the map represents the center of a low pressure system. 2 fronts extend from the center of the low and are labeled front 1 and front 2. Cloud cover has been omitted from the station models. So here we are being asked which map best represents the type of front and direction of movement of these fronts in relation to a low pressure center. All right, well, we know our low pressure center is rotating counterclockwise. So if it's counterclockwise, that means this is going this way. So I better make sure that my symbols are on this side of this front 2, and my symbols are on this side of front 1, the leading edge. So do I have any that are not that way? Yeah, this one. Now I gotta compare between these 2. All right, so the air in here, 76 degrees, 74 degrees, 78 degrees Fahrenheit. Over here, 54 degrees Fahrenheit, 52 degrees Fahrenheit. So if this is the air mass for this front, this air is warmer compared to the air elsewhere in the region. So I'm looking for a warm front on this side, and behind here is cold. So this ought to be a cold front symbol. So I've got choice 1. All right, bell's gonna ring. There we go. All right, let's go to number 2. Numero dos. All right, so a cross section of a weather front is shown below. So this is a cutaway section view. We have a direction of air movement for this air mass. This air mass has been labeled a CP. We have been given an MT. Which symbol will be used to represent this front on the map? So this is the one that's moving this way. So we are focused on this front here. So the front of this air mass is cold and dry. So it should be a cold front only. Choice 1. Had there been one of these here, and then this was the MT, and this was a CP, now you've got the condition for an occluded, because they've met up with each other. Okay? So if the picture looked like that, this would be your answer only under this condition. All right, so now we have reached the end of our notes today, and hopefully you have a slightly better understanding. I want you to continue with the independent practice. If you have any questions, feel free to leave a comment below. I'll try to answer them either there or Google Classroom. Work on this independent practice, use your access points, check your answer key, and we'll do the lab up next. Bye.